In this chapter, we're going to be studying polynomials. In this lesson, we're going to be studying the characteristics of polynomials. All right, hi everybody. So in this lesson, we're going to look at the characteristics of polynomials, okay? Characteristics of polynomials. Now, this is going to be kind of a long lesson. Not that it's particularly mathy, not a lot of like algebra calculations and whatnot in here, but there's a lot of information to go through. Okay, just to kind of lay the foundation, what we're trying to do is create for you an instinct for what certain functions look like, because it makes equation solving easier. It makes working with them easier if you have a bit of an idea of what these things look like. So a polynomial function, okay, is one that can be written like this right here. Okay, so, and I know that looks pretty complicated, but let me just break this down for you. So what we've got here is we've got a whole bunch of ANs here, and these are just numbers. Now, the reason why we've got little subscripts with them is so that you can connect them to the term that they belong to. So a sub n is going to belong to the term that has x to the power of n. A sub n minus 1, okay? And remember, when you're talking about the a's here, the n minus 1, that little subscript there is just an index. It just tells us which number in the group it is. But these numbers can be anything. The little a's here can be anything. So the number that goes with a sub n minus 1 goes with x to the n minus 1. And then dot, 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 all the way down. A sub 2 goes with the x squared term. A sub 1 goes with the x to the 1 term. And even though you don't see the x there, and there's a reason for it, a sub 0 goes with the x to the 0 term. But what happens here is that goes away, so that a sub 0 ends up being the constant, okay, in the expansion there. So don't let the little subscripts there confuse you here. What we're talking about is just a collection of powers of x with coefficients in front of each one here. So it contains only the operations of multiplication and addition with real numbers and variables. The exponents, and this is a big one here, the exponents, okay, must always be a positive whole number. Now that's not to say that you can't ever have fractions in the exponents or negatives in the exponents, but as soon as you do, we don't call that a polynomial anymore. It's something different, okay? And typically when we write the exponents and we write the powers, we usually write them in descending in order. And you know what? Man, does that ever make a difference with some of the other things that we do? What I normally talk, the way I normally talk about this, I'll refer to it as looking pretty. Okay, when you've got a polynomial written and you've got the x's in decreasing order of their powers here, it looks pretty, and because it's easy to work with. Okay, it's when they're all in kind of a weird order, it becomes difficult to work with. That's not very pretty. So here, the graphs of polynomial functions are continuous. Okay, that's an important little point there. They are continuous, which means there's no gaps in them, no breaks, no little jumps. Okay, they're nice, and they're another thing you might say here, and it doesn't quite say it right here, but they're smooth. There's no breaks, and they are smooth. Now, you might wonder, what am I talking about? Smooth. I'll show you an example in just a moment here. In fact, I'm going to show you right now. Here we go. These graphs are not continuous, and therefore they're not polynomials. Okay, so the first one is the absolute value. Whoops, that's not what I meant to put there. I meant to put a little bit of highlighting there. This one here, the first one is the absolute value function. Notice it's continuous. There's no gaps in it, but it's got a sharp corner right there. And polynomial functions don't have that sharp little corner to them. They're smooth, okay? This one right here, the square root function, notice it doesn't even exist over here, so that's not polynomial. And the reciprocal function, that's got a weird sort of an asymptote, okay, showing up right there. So there's a gap in the graph. And polynomial functions don't have gaps. There's nothing wrong with these particular functions. In fact, you'll probably spend some time looking at them, but they don't qualify as polynomials. Okay, so here we're going to have some examples of polynomials and just their functions right here. And so notice you've got the linear, the 2x minus 1, then you got a quadratic, x squared plus 3x plus 2, cubic x cubed plus 9x squared plus 10x. Notice that the exponents on the x, They're always nice, natural numbers, okay? Actually, I probably should say whole numbers because you could include 0 in that. Because you might include, for example, over here, you might look at this y equals 4 and think of that as y equals 4 times x to the 0. You can think of it like that. You typically wouldn't write that x to the 0, right? Because that is just going to be 1. So you really don't need to express that. The coefficients can be quite complicated. They can be any real number here, but the exponents on the x are always going to be nice whole numbers here. So any expression containing the roots, negative or fractional exponents are not polynomial functions. So here we go. These ones are not polynomial functions, and here's why, right? There's the negative exponent right there. No good. Absolute value, remember, this creates a corner. Okay, and we don't like that. We like it when it's nice and smooth here. We've got a denominator here, an x in the denominator. That's no good. This one right here, we haven't actually seen before. Notice that this is kind of a flip of what we would normally have. Compare that to what's up here. Compare these two right here. This is polynomial, part of a polynomial expression. This is exponential. Okay, and we're going to take a look at that in a different chapter. Okay, a lot of interesting things happen. We've got an exponential function here, but it's not polynomial. And then here we've got this square root of x to the 5th, and because of that, because that doesn't work out nicely, that's going to be a what we call a radical function. Now, if you had, for example, though, if you had something that was f of x equals the square root of x to the 4th, that's okay. That would work as a polynomial because that can actually be simplified down to x squared. So you got to be careful. Now, there are some other rules that go along with that kind of simplification. I don't want to take the time in going into that because it's really not going to be significant for what we're trying to accomplish right here. There's all sorts of little rabbit trails we can go off on in all sorts of different directions here, but they're not really going to be beneficial to what you want to try to accomplish here. So here we go. We're going to talk about the degree. Okay, so the degree is the highest exponent on a variable and in a polynomial, and that will be the degree of the polynomial. So you're going to look from term to term, okay, and whichever term has the highest degree, that's the degree that's going to basically be applied to the whole polynomial. And the reason for that, if I can give you a context for this, and in previous courses, I'm positive you talked about degree, but you probably didn't know exactly, why we were doing it. What the degree does is it actually dictates shape. Okay, the degree is going to have the biggest influence on the shape of a graph. Okay, and the term with the highest exponent is going to have the most significant impact on the value of the that you get once you put x's in here. So here we go. Just to name a few here, your constant is simply going to be y equals some number. Its degree is 0, and a good example is just y equals 3, y equals 5, y equals 10, whatever. Okay, and this is just going to be a horizontal line. Okay, this is just a horizontal line. Now, a linear function is y equals ax to the 1. So that's its degree, 1. And that's just going to be a line, kind of looks like that. Quadratic function has got a degree 2. So here's the quadratic term. Okay, this is going to have the biggest impact. When you square a value and then add a number times the value, then plus a constant here, it's the squaring, the term that's getting squared, that's going to have the biggest impact on the value of the function for most values of x. Okay, and so a quadratic looks something like this, and you would have looked at that in a previous course there. Okay, the cubic, the largest degree is 3, so that's the term that's going to have the largest impact for most values of the function, and the cubic is going to look something like this. So it's an interesting little development here. We go from horizontal line to a line at an angle, and then it curves, and then we see a couple of curves there. Now, just some old ideas you've seen before, the x-intercept, okay? That's the point or points where the graph touches or crosses the x-axis, and the y-intercept is the point where it crosses the y-axis. And for most of what we do here, that is going to be the constant in the polynomial. Okay, if you let x go to 0, so for example, we'll use that quadratic there. You've got x squared minus x minus 2. Remember that to get the x-intercept, we're going to to get the y-intercept, we let x go to 0. To get the x-intercept, we let y go to 0. And in this case right here, if you let x go to 0, this term goes to 0, so does this term. And all you're left with over here is just that constant. So that's typically going to be the y-intercept. The leading coefficient, okay, the leading coefficient is the coefficient of the greatest power of x. Okay, so here's the highest degree term. That -2 is the leading coefficient, and then you've got this constant over here. Now, the leading coefficient typically gives us a stretch and orientation. Okay, and usually we associate, for example, negative with down, positive with up, and we're going to need to kind of flesh that out just a little bit more later on here. But yeah, and then the stretch, the value of that leading coefficient, whether it's a 2, a 3, or 4, or 5 here, that kind of affects how quickly it grows, how quickly it kind of swoops away from the x-axis and then swoops back down again. But really for us right now, just getting a sense of what's going on here, the more important thing is, we typically associate negative with down, positive with up. Okay? End behavior. Here's another way of talking about polynomials, end behavior. And basically what we talk about end behavior, what we're doing is we're describing what quadrant you start in and what quadrant you end in. Now, but bear in mind here, and this is an important little point here, these are always read, okay, left to right. Okay, so when I talk about what quadrant did you start in, well, that could only be quadrants 1 or 3, because those are on the left-hand side of the coordinate plane. And where you end can, sorry, that should have been 2 or 3. I can't believe I think I even said 1. Wow. As soon as I wrote it, I was looking in the wrong spot here. I'm sorry. It can either start in quadrants 2 or 3, and it will end in either quadrants 1 or 4. Okay? So that's how you talk about end behavior. You're either going to say 2 to 1 or 2 to 4, 3 to 1 or 3 to 4. That's what we're referring to. Now, that doesn't mean that it couldn't wander through other quadrants here, but we're talking if you go really, really far left or right, where are they? So, for example, in this first one, this one clearly starts in quadrant 3. Now, granted, it goes up into quadrant 2, it dips down into quadrant 4, but then it's going to end in quadrant 1. Whereas over here, this one also starts in quadrant 3. No, sorry, I was just about to write the Roman numeral, but I was going to write the number here, 3. But this one goes up into quadrant 2, up into quadrant 1, and then it comes down into quadrant 4, 3 to 4. Okay? And that's what we're referring to. That's what we mean by end behavior. Okay, turning points. What are the turning points? Well, it's the points where the graph changes direction. Okay? So the turning points occur at maximums and minimums. Okay, little maximums and minimums here. So for example, in this particular graph right here, as you read it left to right here, it goes up, hits this little maximum here, drops back down. So there's one turning point, and then it drops down, hits a minimum, and then turns and goes back up. So we talk about changing directions. What we mean is vertical, in terms of vertical motion. Whoops. Because we assume we're always moving left to right, horizontally. So the question is, where do I turn directions? Well, it's where I go from going upwards to going down, or from going down to going up. So this graph right here, when you read it moving to the right here, okay, it hits this maximum and then it drops back down. This has only got one turning point. Now, making some connections here, and this is really where we get to the important point, the real kind of thrust of this particular lesson here. The turning points, how many turning points does each kind of a function have here? Well, a quadratic function will always, always, always have a turning point. One, and it should say contain, it says on turning point here. It should say one, whoops, sorry, that's not what I meant to write there. I meant to write, oh, I'll just whatever. One turning point. Now, x-intercepts might change here. This first one's got no x-intercepts, but one turning point. One x-intercept, one turning point. In fact, they're the same. Two x-intercepts, but again, one turning point. Quadratic function always has one turning point. A cubic function, on the other hand, okay, a cubic function contain at most two turning points, but it might have zero turning points. And that is going to start to become fairly true of our odd functions here, okay? Our odd functions here can always go down to zero in terms of turning points here. Now, that's not to say, okay, when we say at most two turning points, it's not to say that it could have one. If it had one, it would be quadratic, okay? It's got to have two or zero, and then it's in its cubic here. So just to take a look at some examples of what that looks like. This first one here has got one x-intercept, and arguably it has no turning points. What happens here is it kind of comes up, it sort of levels out, and then keeps going up here. But this one has got, this one's got two x-intercepts, and it's got two turning points, one right there and one right there at that x-intercept. Here, this one has three x-intercepts, and it's got two turning points, a little maximum there and a little minimum. So, characteristics of polynomial functions. We're going to try to put these together here. So, a linear function has degree 1. It could look something like, sorry, forgot to switch over. It can look something like this, or it can look something like this. Those are what your lines look like here. If the slope is positive, it goes up to the right. If it's negative, that should say falls to the right. Okay. If you go to the left, it goes up. Its domain is going to be x is an element of the reals, and its range is going to be y is an element of the reals, okay? Unless it's a horizontal line. But in that case, the degree is going to be 0. It'll be a little different. The quadratic, okay? Now, this one's got a positive leading coefficient, and remember, I associate positive with up. That's why this thing opens up. In fact, I'll give you a little clue here. If it's got a positive leading coefficient, it's going to open up. But for a quadratic, if it's got a negative leading coefficient, it's going to open down. So you can kind of associate the happy face and the sad face. Positive sign up, negative sign down here. Just whatever. It just kind of gives you an idea here. This one goes from quadrant 2 to quadrant 1. Quadrant 2, quadrant 1. It contains a minimum value at -9. I can read that off the graph right there. There's that vertex, that minimum point. It's got one turning point. Its domain, and we're referring specifically to the one that we're looking at right here, is going to be all reals. Its range, though, is going to be greater than or equal to -9. Okay? These two are going to be related. When I identify a maximum or a minimum on a quadratic, that is going to be related to the range. Okay. Here's another quadratic, degree 2. Notice that the leading coefficient here is negative, and that's just like I said, that means it's going to open down. It contains a maximum at +4. It's got one turning point. This one is going from quadrant 3 to quadrant 4, and I know that it goes through quadrant 1 for a little bit, but that's not where it ends. The domain, all reals once again. And again, the range is linked to that maximum/minimum value here. In this case, because this is a maximum, because it opens down, it's got a maximum, the range is going to be y is less than or equal to 4. Oops. Let's take a quick look at the cubic functions. So cubic functions, degree 3, if it's positive, because it's positive, what I want you to notice here is that its general motion is to go up. It starts slow and moves up here. Whereas down in this next one, if it's got a negative leading coefficient, the overall motion is down. It starts high, ends low. So this one goes from quadrant 3 to quadrant 1. And this one goes from quadrant 2 to quadrant 4. And I have no idea why I'm jumping back and forth between Roman numerals and the Arabic numerals here. I'm sorry about that. I just don't know why. This one's got 2 turning points. Its domain is all reals, and it turns out its range is going to be all reals too. Okay, end behavior here, we just said it. It's going to go from quadrant 2 to quadrant 4. It's got 2 turning points. The degree is 3. And the x-intercepts in this case are -2, looks like -1, and +2. You have to look at the scale. Don't look at the little tick marks there, because the little tick marks are, it looks like we're dividing the numbers into thirds there. You just got to be careful with that. Okay. So there's a whole bunch of information here. And I suspect a bunch that's going to be sort of new. This shouldn't be new, though. The fact that we can relate roots to zeros to x-intercepts here. Okay, remember that when you've got a function here, set equal to 0, if you factor it and get the roots of that equation here, those correspond to the x-intercepts of that graph. The graph is going to go through -2 and +3 here, okay? So when you see it going through x equals -2, that means x plus 2 is a factor. Just like if you see x equal to 3 on the graph, that means x minus 3 is a factor. Now, that in and of itself should actually, for some of you, all of a sudden, there should be a, oh, wait a minute, you mean if I graph something, I can look at the graph and use that to factor that equation? And the answer is yes, as long as you know what you're doing, as long as you take out, for example, common factors first, and then look for your x-intercepts. Yep, that's what that'll do. So that's a great little tool here. So for our cubic here, if it goes through -1, that means x plus 1 is a factor. This one goes through x equals 2, so x minus 2 is a factor. Goes through x equals 4, so x minus 4 is a factor. This thing has 2 turning points, so it's going to be a degree 3. It's got 3 x-intercepts, and because the overall motion is down, I know that it's got a negative leading coefficient, even though I don't have the equation for it. Okay? So now let's keep going here. So just a little summary, Degree is the highest exponent, or the number of times it changes directions. Actually, the number of times it changes directions, plus 1. Whoops. Plus 1. Right? Because if it's a degree 3, it's going to change directions twice. So you need to add 1 of that. The degree is the maximum number of x-intercepts a graph can have. Yep. Degree and the leading coefficient tell the end behavior, and I hope you're kind of getting a sense of how that works here. We're going to summarize that up in just a second here, but yep. And the y-intercept is the constant. So here we go. Let's take a look at some here. We're just going to, okay, I can see everything almost on the screen here. So linear function, okay, then we've got the examples of the linear, the quadratic, and the cubic. So now we're just going to fill in the blanks here. So a linear is degree 1. Whoops. Sorry, I got the wrong thing on there. A linear is degree 1. Quadratic is degree 2. Cubic is degree 3. The leading coefficient, in this case, it's the coefficient of the x to the 1 term. Here, it would be the coefficient of the x squared term, and in that case, if I don't see a number in front, it's 1. And here, the coefficient in front of the x cubed term is going to be -1. My x-intercepts, well, what I would need to do here is pull out my calculator and solve those. So I'm going to have to pull out my calculator. And then I graph them. And I'm going to use the 0 feature on the calculator, okay, the 0 function to find the x-intercepts here. So in this first case right here, when I look for the x-intercept there, I'm going to get -2/3. Okay, and I'm kind of assuming at this point that you've gone through like 2 other courses in high school here, where you have used your calculator to find x-intercepts and that you're comfortable with this. For my quadratic here, my x-intercepts are going to be 0.8 and 7.2. And for my cubic, I got -3.8, -1.3, and 1.0. Okay, so, and like I would have guessed here, for my linear function, I got 1 x-intercept. For my quadratic, I got 2. For my cubic, I got 3. That doesn't necessarily mean, for example, for my quadratic that I was going to get any. I could have gotten 1 x-intercept or even none. But the maximum I could get there is 2. For a cubic, just like just like I was saying there, the maximum I could have there is 3. Certainly couldn't have any more than that. The constant term in this case was 1. The constant term here is 6. And in this case here, the constant term is 5. Which means, by the way, that corresponds to our y-intercept. This would be the y-intercept here, this would be the y-intercept here, and this would be the y-intercept here. End behavior. Okay, this is a positive linear, which means the graph is going up. So it's going to go from 3 to quadrant 1. Okay, a quadratic that's positive opens up. That's going to go from quadrant 2 to quadrant 1. A negative cubic, it's going to wiggle a little bit, but it's going to ultimately be going down because of the leading coefficient. So this is going to go from quadrant 2 to quadrant 4. Okay. The domain, well, the domain for my linear is going to be all reals. The domain for my quadratic is going to be all reals. And the domain for my cubic is going to be all reals. The range for my linear is going to be all reals. The range for my quadratic, though, is going to depend on the minimum number that I get. Okay, so I'm going to go back to my calculator and use the minimum feature to find that value. And it turns out in this case it's going to be -10. So that means that my range is going to be greater than or equal to -10. And for my cubic, my range is going to be all reals. In fact, you're going to notice that it's going to be all reals, except for the range of a function that's got an even degree. As soon as it's got an even degree, then it's either going to have this ultimate maximum or minimum here. For the linear function, the number of turning points was 0. For the quadratic, it's 1. And for the cubic, it's 2. I was about to write 3 there. As soon as I said cubic, I was about to write 3 here, but the number of turning points is going to be 2. Okay, so now we're going to use the graphs here to answer the questions below. So we're probably going to have to kind of slide back and forth here. So here we go. If a is greater than 0, so that's typically the leading coefficient we're talking about here. It's got a degree of 3. It's got 1, 0. A constant of 1 is graph number. So if it's degree 3, now degree 3 and a is greater than 0 means it's going, it's moving up. So it's a cubic that's moving up. It's got 1, 0. A constant of 1 in the graph, and that is going to be number 4. Okay, so notice it's got 1, 0, it's moving up, and because it's got 2 turning points here, that's going to be a cubic. 2 is a cubic where the leading coefficient is negative, which means it's going to be going down. Whoops. So it's going to be going down. And then it's got a constant of 2. So a cubic that's going down, well, actually, graph number 2 is the only cubic that's going down, and it turns out it does have a constant 2. It's got a y-intercept of 2 there, so that's just going to be graph number 2. Whoops, man, I keep forgetting to switch back to the pen there. A negative leading coefficient with a maximum of 4 and one turning point is a quadratic, so we're looking for a quadratic that opens down. Well, there we go. Number 5 is the only one that's a quadratic that opens down. Question 4 says a positive leading coefficient and a degree of 2. Okay, so it's a quadratic. It opens up and no x-intercepts. Okay, no x-intercepts, a quadratic with no x-intercepts. Well, it can't be 3. Okay, it's got to be 6. Got to be 6. Okay, and there we go. That's the end of that question here. So the next question we're looking at here is we're going to complete the table, the type of graph. Okay, so let's just run through this here. So this first one here, because it's got 2 turning points, it's a degree 3. The sign of the leading coefficient, because the overall motion is down, it's going to be negative. It's got 2 turning points. Its x-intercepts are going to be -3 and +1. I can see those right there and there. I can just read those right off, which means its factors are going to be x plus 3 and x minus 1. The y-intercept is the constant. That is going to be where it crosses right there. Now, on the scale, it looks like it's going up by 2s. So best guess, that's going to be -3. The domain is going to be all reals, and my range is going to be all reals as well. Okay. Slide it up just a little bit here. This next one is also a degree 3 because it's got 2 turning points. This time, though, it's because the overall motion is up, it's going to have a positive leading coefficient. It's got 2 turning points. The x-intercepts are -4, looks like -3, and +2, which means it's going to have factors here, x plus 4, x plus 3, x minus 2. Those are the factors all multiplied together. Oh, boy. Okay, so it looks like we're going up by 5s. That's a rough guess here. I'm not 100% sure what the y-intercept of the constant was going to be, but it's going to be that number right there, and we're just kind of guessing at it. But again, the domain is going to be all reals. The range is going to be all reals. Okay, what's next? Okay, we got a quadratic here. So this is going to be, I believe it was degree 2. Okay, this one is got a negative leading coefficient because it opens down. Okay, I don't even remember what this number of turning points. Okay, number of turning points here was 1, and it's got a maximum value of 9, it looks like. My x-intercepts here are -3. Whoops, -3. Wow, that's not even vaguely what that looks like. Okay, it's going to be -4 and +2, which means our factors are going to be x plus 4, x minus 2. My y-intercept, or my constant, is going to be +8. My domain, and basically with all polynomials, the domain is going to be all reals. But my range, because this is an even power, it opens down, is going to be less than or equal to that maximum value of 9. Okay, and there you go. Let's take a look at the next one. Okay, given the following equations, complete the following table here. Okay. Oh, and this is where we're going to end here. So I know there's a little bit of a break here, but that's okay. We should be able to fit this all in. So first of all, what's the type of function here? Well, I've got a linear times a linear times, I've got x times x times x. This is going to be a cubic. Okay. The leading coefficient is going to occur when I multiply this by this by this. So 4x times x times x, that's going to be 4x cubed, so 4. The degree is going to be 3. Because the leading coefficient is positive, that means this thing is going to move up. So it's going to go from quadrant 3 to quadrant 1. Now, my x-intercepts, remember, I get my x-intercepts from the zeros, okay? So that's going to be 4x plus 2 equal to 0, okay? So 4x plus 2 equals 0, x minus 3 equals 0, x plus 10 equals 0. That's going to end up giving me x is equal to -1/2, x is equal to 3, x is equal to -10. So there we go, -1/2, 3, and -10. And the constant is going to be when you multiply the constants for each one of those together. So 2 times -3 times 10, that is going to give us -60. Okay, I'm going to erase this because I'm going to probably need that space again. So for the next one, this one here, this factor is being squared, and it's got another factor here. So that's going to be cubic as well. Okay. The leading coefficient, well, x times x times x, so it's x cubed. But then there's this negative out front here, so it's going to be -1. So the degree is 3. This is a negative cubic. It's going to go down. So the end behavior is going to be from 2 to 4. Now, its x-intercepts here, I've got x plus 1 could equal 0, or x minus 2 could equal 0. So x could equal -1 or 2. And notice that I've only got 2 x-intercepts for this cubic. That's okay. But it certainly couldn't have more than 3. And if I want to figure out what the constant is, I just got to multiply the constant pieces together. So it's going to be -2 squared because of that right there. So -2 squared is 4. Multiplied by 1 is still 4. Multiplied by -1, that coefficient up front here, that is going to give me -4. Okay, this guy right here is linear. Its leading coefficient is -1/2. It's got a degree of 1. Okay. So remember, the Math 10 course is focused primarily on these kinds of linear functions here. Because it's a negative odd degree, it moves down. So it's going to go from quadrant 2 to 4. The x-intercepts, well, in this case right here, we'll just erase what's up here right now. There's only the one real factor there, right? So what we'll do here is set that equal to 0. So negative 1/2 x plus 5 is equal to 0. So negative 1/2 x is equal to negative 5, and x is equal to positive 10. Okay, that's it. And the constant, well, I can see it right there. It's just going to be 5. This next one is a quadratic. Its leading coefficient is 1, so that means it's going to be positive. It's going to open up. Degree is 2. So because it opens up here, this is going to go from quadrant 2 to quadrant 1. X-intercepts. Well, this time right here, the x-intercepts, it's a matter of factoring this quadratic to solve it. Because remember, what I do is I'm going to set it equal to 0. I'm going to solve it. So x squared minus 3x minus 2. And I'm hoping that it factors nicely here. Let's take a quick look here. And it won't. It won't here. So I'm going to have to pull out my calculator and have a quick look. And from looking at my calculator, I see that I've got negative 0.6 and 3.6 as my x-intercepts. And the constant here is simply going to be negative 2. Okay. And now one last little question here. What happens if it's a little bit less specific? Well, in this case, I've got x minus a times x plus b. Okay. So this is definitely a quadratic. It's got 2 factors, so that's quadratic. It's got to have a leading coefficient. Well, x multiplied by x is just 1x squared, so it's going to be 1. The degree will be 2. Because it's positive 1, this thing opens up here, so this is going to go from quadrants 2 to quadrant 1. My x-intercepts here are going to be where the 2 factors, I'm just trying to clean it up top here, so that we can do that little bit of math. So I have got two different functions here. It's going to be x minus a is equal to 0. X minus b is equal to 0. So x is either equal to a or x is equal to b. So there we go, a or b. Oh, sorry. I'm sorry. Plus b is equal to 0. So that would be negative b. My mistake. And when you multiply those 2 constants together in this expression, negative a times positive b, you are going to get negative ab as your constant. Okay, a lot of little details, an awful lot of little details, and I totally understand that. So this requires a little bit of memorization to get a sense of how things go here, because from this point on, we kind of apply that and we make use of what we've learned here. So you do want to spend some time and make sure that you're understanding what we've done. You can look at a polynomial and make some predictions about its behavior or its graph before you actually look at it.